All right? So, good. Now we're going to do the same for the test set results. So I'm just going to copy everything here and paste that in a new code cell right here. And so now we're going to do the right replacements in this code in order to visualize this time not the training set results, but the test set results. And so obviously the first thing we need to replace here are the coordinates of the real observations, because these are the coordinates of the employees in the training set, and we want the coordinates of the employees of the test set. Therefore, here we have to replace obviously xtrain by xtest and then ytrain by ytest. Okay, so these are for the real observations with the numbers of years of experience and the real salaries of the test set. And now, according to you, do we have to replace something here? In PLT plot, xtrain regressor.predict xtrain. According to you, do we have to replace xtrain by xtest and the same xtrain by xtest? Well, that's kind of a trick question, because remember that the regression line that we get is actually resulting from a unique equation, and therefore the predicted salaries of the test set will be on the same regression line as the predicted salaries of the training set. And that's why here we actually don't have to replace xtrain by xtest here and here, okay? You would actually get the exact same regression line whether you plot the coordinates of xtrain and the predicted salaries of the training set, or xtest and the predicted salaries of the test set. You can check, but that's because the regression line in a simple linear regression model results from a unique equation, and we therefore end up with the same regression line. Okay, so no need to replace anything here. And finally, we will just replace here training set by test set. And there you go. Now we're ready to visualize the training set results and the test set results. So let's first run the cells we haven't executed before. So remember, we executed up to the training. So now we have to execute this one to indeed get the vector ypred of the predicted salaries of the test set. So there we go. We now have ypred. And so now we're going to first execute this to visualize the training set result. And we're going to obtain now a nice 2D plot with indeed the real salaries in these red points here, and of course our beautiful regression line containing the predicted salaries. And we clearly see that this regression line was calculated so that it comes as close as possible to the real salaries. And of course, for each of the years of experience here, in order to get the predicted salary, you have to project the year of experience to this blue regression line. So for example, the predicted salary corresponding to 8 years of experience is about, $100,000 per year. Okay, so that's how it works. And so we can clearly see that our predicted salaries are very close to the real salaries, for most of them. But that's on the training set. Remember, that's important because our model was actually trained with these observations, with these years of experience and salaries. Now, what we would like to observe is if we have the same result, the same closeness of the regression line to the real salaries in the test set with which the model wasn't trained. We want to evaluate it on new observations. And that's exactly what this new graphic will tell us, because now we're about to plot, this time, the real salaries of the test set and the predicted salaries of the same test set. So there we go. Let's run the cell and let's see if we're still close to the real salaries even for new observations. And yes, absolutely, our predicted salaries, which are of course on the blue line once again, are very close indeed to the real salaries. So our model, our simple linear regression model, was able to do a wonderful job at predicting new observations. So congratulations, that's very exciting. You built a very successful first machine learning model. However, just remember that the reason why we get such a good regression line here is simply because there was a linear relationship in the dataset between the features and the dependent variable of the dataset. In other words, we had a perfectly linear dataset. In other words, we had a dataset with linear correlations. And what I want to make sure you understand is that these beautiful results won't happen for any dataset, because of course you'll get to work on datasets with nonlinear relationships, and for these datasets you will need a nonlinear model. And that's exactly why in this part 2 regression we will also study some nonlinear models, which you will see will be polynomial regression or SVR, which will allow you to get amazing results for datasets having nonlinear relationships. But for this dataset, we clearly had linear relationships, and that's why a linear regression model was perfectly fine, but I just wanted to highlight this. Okay? So congratulations once again. I hope you're very happy and excited to have built your very first machine learning model. Now we're going to increase the difficulty a bit, because in the next section we will build a multiple linear regression model, meaning that instead of having one feature, only one independent variable, we will have several of them. And that's exactly the difference between simple linear regression and multiple linear regression. Simple linear regression is when you have only one feature, and multiple linear regression is when you have several features. So take a good break now, and as soon as you're back with your energy, let's implement our second machine learning model in the next practical activity after Kirill's intuition lecture. And until then, enjoy machine learning.